A very good morning all of you. Welcome to the lecture number 41. In lecture number 41 we are going to discuss about JK, D, T flip-flop as well as asynchronous inputs. Asynchronous inputs for flip-flop and their usage. Okay. Before we start the JK or D or T flip-flop, let we'll see what is the need for this flip-flop. If you look at your SR flip-flop, as you know, S and R and Qn plus 1 truth table. When both are 0, 0, it will be in memory state, or you can say in the previous state. When 0, 1, it will be reset state. That means it will be 0, and 1, 0 will be set state, and it will be 1 state. And when you make both 1, it is a invalid state. So, but in real time situation, when you design the real digital circuit, we cannot impose a restriction on two input that those two inputs should not use 1-1 combinations. So as a result, there is a need for the circuit, another kind of a circuit, another flip-flop, which allow both 1-1 combination or 0-0 combination if you take SR flip-flop based on NAR latch. So we need to design one more flip-flop where we can give 1-1 or 0-0 combination also as a input, and which produce a very useful result. That new flip-flop is called JK flip-flop. This is a scientist named Jack Kilby is the inventor of this flip-flop. That's why the name is given as JK flip-flop. In JK flip-flop, we are going to use 1-1 combination, and this 1-1 combination is going to produce a very interesting result. This result is the key for designing counters or designing many sequential logic circuits also. Now we'll see how this JK flip-flop is going to allow this particular input state and going to produce a useful result for us. Now let's take the JK flip-flop. So for JK flip-flop is same as SR flip-flop with a slight modification. Let's take SR flip-flop first. Clock are enable, it's going to be S and R. This is the SR flip-flop, as you know. We are going to do a small modification here. That modification is going to allow us to use the 1-1 combination. What I am going to do is I am going to take the Q output and give it as a input for the R AND gate. Similarly, I am going to take Q bar output and give input as a S AND gate. This is your Q and this Q bar as usual. Now the extra thing what we did is we just added one feedback loop, Q bar to S and Q to R AND gate. Now we are going to analyze this circuit. Now I can change these names as J and K. Okay. Now we'll see how it is going to use the all the combination. Let's take first case. Let's take case number 1. Let's take clock or enable is 0. First we will say clock or enable is 0. When your clock or enable is 0, this 0 will be applied here and here. When this 0 is applied here and here, this NAND gate don't have to consider other two inputs. Here also other two inputs is going to produce output 1 here and output 1 here. So in this case you are applying 1-1 input to the NAND latch. So 1-1 input for the NAND latch is a memory state. It will be in the memory state. That means when the clock or enable is 0, your circuit will be in the same state, whatever the state you are having in the previous state, irrespective of your feedback. Irrespective of your feedback, your Q and Q bar as well as your J and K inputs also. This is the first condition we are supposed to consider. Then it is very clear that when clock or enable is 0, your circuit remain in the previous state for forever. Now I am going to consider clock equals to 1. When clock equals to 1, I am supposed to consider the all possible combinations of j and k. Now we'll see one by one all the possibilities of j and k in a moment. Now let us consider the second case. Now consider second case where I am going to keep my clock 1 now onwards. I am going to make my j is 1, k is 0, and I am assuming my previous output is 0 and q bar will be 1. Similarly, for the same condition, I am considering my previous outputs are different. J is 1, k is 0, and I am considering q this time as 1 and q bar as 0. Now we will try to analyze. So first I am going to analyze this situation with the red color pen. So I am keeping this is 0 and this is 1, and my j is 1, k is 0, and clock is 1. This clock 1 will be applied here as well as here. Now if you consider this is 1, this feedback will go here and applied here, and this is 0, this 0 comes from here and applied here. This all ones will becomes 1, 1 bar will be 0, and 1 into 0 will be 0, 0 bar will be 1. As you know, 0, 1 for the NAND latch will be set state. That means you are going to get your next state as set state, that is 0 to 1. That means your 0 becomes 1, and the same way is going to become 0. Okay, this when you consider the first case, assuming previous output as 0. In the second case, now you are assuming your previous output as 1. So I am considering previous output as 1, and this becomes 0 automatically. Now again you do the same analysis. Now this time this 0 travel back and applied here. Instead of 1 it will be 0, and here similarly this 1 will travel back here and applied here as 1. Now in this case 1 into 0 into 1 will be 0, 0 bar will be 1, 1 into 1 into 0 will be 0, 0 bar will be 1. When you apply 1 1 for the NAND latch, it is going to be in the same state. That means it is going to be in the same state as your previous state. There is nothing but 1 here. So it means whenever you apply j equals to 1 and k equals 0 and clock is enabled, you are going to set your output to 1. So this is nothing but set condition for the JK flip-flop. Now we are going to see the case 3 in a moment. Now let us see the case 3. For case 3 I am considering again clock is 1. This time I am considering my j is 0 and k is 1. Same I am considering my previous output as 1 and q bar will be 0. This is the first consideration, and second consideration I am taking my clock as 1, j is 0, k is 1. At the same time considering my previous output this time as 0, and this will be 1. Now we will analyze the circuit. First we will start with this one. So here we assume previous output as 1, and this will be 0. My j is 0, k is 1, and clock is 1. This will be 1 here and this will be 1 here. If you look at here, this 0 will travel back here and apply here, and this 1 travel back here and apply here. This all ones will be 1, 1 bar will be 0 here. Here 1 into 0 will be 0, 0 bar will be 1 here. If you look at here, you are applying 0 1 to the SR NAND latch, that will reset your output. It is going to reset your output. So previous output is 1, it is going to be 0, or you can say it is resetting your output to 0. This is when you consider previous output as 1. Suppose if you consider previous output as 0, so I am considering a different ink. So I am considering this time previous output as 0 and this is 1. Now if you look at here, the same thing, the 1 will travel back here. Instead of 0, 1 will be applied, and this 0 will travel back here, and instead of 1, 0 will be applied here. So 1 into 0 into 1 will be 0, 0 bar will be 1, the same as previous. And if you look at here, 1 into 0 into 1 will be 0, 0 bar will be 1. If you look at here, you are applying 1 1 to the NAND latch, that will be memory state. That means it is going to be in the same state. Your Qn plus 1 will be in the Qn, this is nothing but 0 state. So when you apply j equals 0 and k equals to 1, irrespective whether previous output is 1 or 0, it is going to be reset the output to 0 state. That means j equals to 0 and k equals to 1 is a reset condition for the jk flip-flop. Now we'll see the case number 4. In case number 4, I am going to take my clock as usual 1. This time I am going to take j is 0, k is 0, and first I am assuming my previous output as 1 and this is 0. For the same condition I am going to take clock 1, j 0 and k 0, and this time considering my q as 0 and q bar will be. So let's start with this condition, assuming previous output is 1 and this will be 0, my j is 0, k is 0. So if you take the feedback from here, this will be 0. If you take feedback from here, this will be 1. And clock is 1, clock is 1. This will be 0 into 0 into 1 will be 0, 0 bar will be 1. Here also 1 into 0 into 1 will be 0, 0 bar will be 1. If you look at here, it is applying 1 1 to the NAND latch. That means it will be in the memory state. Whatever the previous output you are going to have, it will be in the same state. This is for if you consider previous output as 1. Suppose if you consider previous output as 0, now we'll see. So I am considering my previous output as 0 here, then this will be 1 here. Now this 1 will travel here and applied here, and this 0 will travel here and applied here. Now if you look at here, 1 into 0 into 1 will be 0, 0 bar will be 1 once again. Here also 0 into 0 into 1 will be 0, 0 bar will be 1 once again. So when you apply 1 1 to the NAND latch, it will be in the same memory state. So you are going to have memory state, that means your Qn plus 1 will be a Qn. So it means whenever you apply j equals 0 and k equals 0, so whatever the previous output, it will be in the same state. Your next state will be your previous output, or you can say it's a memory state for the JK flip-flop. Now we'll see the last and most important condition for the JK flip-flop. So please listen, this is very very important. So now I'm considering my j equals to 1 and k equals to 1, clock also 1. So this is very very important, which we did not use previously in the SR flip-flop. Now same way I'm going to consider my output as 0 and this will be 1. Similarly I'm considering the second case, j equals to 1, k equals to 1, clock also 1. This time considering my q as 1, q bar will be 0. First we'll start with the first case, assuming. So now I'm going to consider my q as 0 and q bar is 1. Now if you look at here, j is 1 and your k is 1 and your clock also 1. Now this 1 travel back to here and this 0 will travel back here. If you look at here, all 1s will becomes 1, 1 bar will be 0. And if you look at here, 1 into 1 into 1 into 0 will be 0, 0 bar will be 1. Now when you apply 0 1 to the NAND latch, is going to set your flip-flop. That means you are going to change your Qn plus 1 to 1 state. Okay. Now this case is over. Now we'll try to see the second case. In the second case, I am considering my q as 1 and q bar as 0. Now this 0 will travel back here and apply here, and this 1 travel back here and apply here. So this will be 1 into 1 into 0 will be 0, 0 bar will be 1 here. This will be all 1s, 1 bar will be 0 here. When you apply 1 0 to the SR NAND latch, it is going to reset your output. That means you are going to get Qn plus 1 as 0. If you look at carefully both the results, when j equals to 1 and k equals to 1, whatever the previous output, that is getting complemented. Here also it is complementing. Here also it is getting complementing. If it is 1, it is becoming 0. If it is 0, it is becoming 1. So it means when j equals to 1, k equals to 1, whatever the output, previous output, that is going to get a complement, or you can say Qn bar, or it's clearly you can call it as a toggling. It's going to toggle between 0 1 when you apply the j equals to 1, k equals to 1. So this is how we have solved the problem of using 1-1 combination in the JK flip-flop. Now we'll try to summarize all at one place and then we'll try to simulate this circuit to show the results of toggling and all. If I summarize all this at one place, so your JK flip-flop will be your J here and K here, and you're going to have a clock, then Q, then a Q bar. So this is a positive edge triggered. Now your truth table will have a J, K, you are going to have a clock here, and you're going to have a next state here, UN plus 1. When clock is 0, you don't have to consider the JK inputs, it will be in the memory state. Whatever the previous state you're going to have, the same state will be continued. When the clock is enabled, that I am making it with the arrow mark. When J is 0, K is 1, it is going to reset your output to 0. Similarly, when the clock is enabled and you apply J is 1, K is 0, it is going to set your output to 1. Similarly, when clock is enabled and both the inputs are 0, 0, it is going to be in the memory state. When clock is 1 and both inputs are 1, 1, it is called toggle state, or you can mention it as Qn plus 1 will be Qn bar. So this is a very important part. So this is a very important condition. Whenever you give J and K equals to 1, whatever the output you are going to have, that will be toggled to the next state or going to complement to the next. If it is 0, it becomes 1. If it is 1, it becomes 0. Why we call this as a toggle? We will see in a moment. When you analyze the circuit, you will understand why it is called toggling instead of complementing. Now let us simulate the JK flip-flop in multisim software. Now you can see here this is a SR latch only, SR flip-flop only, extra feedback connections are established. Now we'll try to run the simulation. So if you look at here, the first you are enabled your input, that is your clock is enabled. When set is 0 and reset is 1, set is nothing but J and reset is nothing but K. When J is 0 and K is 1, it is going to reset your output to 0. When you apply both 0, 0, if you look at here, when both are 0, 0, it will be in the same state or it will be in the memory state. If I make my set input as 1, it is going to set my output to 1. You can see it is setting my output to 1. If I make both 0, 0 again, it will be in the same memory state. If I make my reset input once again 1, it is going to reset my output to 0. So this is with set condition, reset condition. Set condition will be J equals to 1, K equals 0. Reset condition will be J equals 0 and K equals to 1. Now if I make my enable low, whatever the change you do at the J input side, whether you set the flip-flop or reset the flip-flop, is not going to affect the output. So it means when the clock is disabled, it will be in the memory state. So if you look at here, if I make my reset 0 and set 1, if I make clock enable by applying 0 to 1, it's going to set my flip-flop to 1 state. You can see here. So these are the 3 cases, 0, 1, 1, 0 and 0, 0 case. Now we are going to see both 1, 1 case. So let me disable the circuit. Let me make both 1, 1. Now if you observe carefully, you can see here your output is toggling between a 0 and 1 because you are applying input forever. You are not applying for a short period of time. You are applying continuously. Your J is 1, K is 1 for continuous period. So as a result, enable is 1. So it always try to toggle between 0 to 1. As you've seen, as long as your inputs are 1, 1, your output going to toggle between 0 and 1. So that is the reason instead of getting complemented, we always say that J equals to 1, K equals is going to toggle the output. If it's 0 is there, 1. If 1 is there, it becomes 0. So this is a toggling condition at J flip-flop. This will be useful in designing the counters. Now you have verified the working of JK flip-flop in multi-sim software. Now if you look at here, if you compare here, it is nothing but your JK flip-flop is identical to SR flip-flop. Only difference is in case of JK flip-flop, whenever 1 1 comes, your output going to toggle. And in case of 1 1 SR flip-flop, it's a not a valid input. That's the only difference. Rest will be 0. Your J is equivalent to S and your K equivalent to R. When J equals to 1, K equals 0 and S equals to 1, R equals to 1. S equals to 1, R equals 0. Both conditions will set the flip-flop to one state. Similarly, J is 0, K is 1, S is 0, R is 1. Both the conditions will reset your flip-flop to 0 state. Similarly, J is 0, K is 0, S is 0, R is 0. These two conditions also will keep your flip-flop in the memory states. Only should remember this particular difference when in 1 1 is given as an input for the flip-flops. This is all about your JK flip-flop. Now we are going to see the most important point in the JK flip-flop. This will be asked in the interviews. So in JK flip-flop, the most asked question is a race around condition. In race around condition, your output will race in response to the clock signal. We'll see how it is going to race along with the clock signal. Suppose this is your clock signal, let us assume. Please listen, this condition will occur only when you use the level triggered clock. When you use a level triggered clock or your circuit, whenever your JK flip-flop is given to a level triggered, instead of edge trigger, if you give the level triggered clock for the JK flip-flop, you are going to encounter the race around condition. Let's take this is my clock, and this entire level my circuit will be active. Now let's take J equals to 1 and K equals to 1. This is my J and this is my K. Let us assume this is my Q. So till this place your clock is disabled. That means let us assume the previous output is in, let's say 1 state, let's say 0 state. So till this place your clock is in low state, it will be in the memory state. After this time your clock is enabled. If you look at any other place along this particular direction, you look at here, during this period, this small period, your J is 1, your K is 0. That means going to set your flip-flop to 1. And after that, if you look at here, your J is 1, K is 1 for this entire period. From this onwards till this place, your J is 1 and K also 1. So during this period, your output first goes to 0. And after that, you will see the J and K all 1, and as well as clock also 1. It again toggle to 1, again toggle to 0, again toggle to 1, toggle to 0. So this process will take place within that short period of your clock pulse. After this period gets over, so it will take clock is 0. When the clock is 0, it will be in the memory state. So if you look at this period, during this period your clock will race. During this period your clock, if you look at this period, during this period your output will race between 0 to 1 and 1 to 0. That's why this is called a race around condition. This race around condition can be avoided by using a short enabled clock pulses, or you can say edge triggered clock pulse. When you give the edge triggered clock pulses, you are going to avoid this particular condition of a race around condition. There is another way of doing it that you figure it out by going through the books. Okay, so this is all about your race around condition in JK flip-flop. Now I am going to design the another two flip-flop which I told in the starting of this lecture, D flip-flop and T flip-flop. Let's take D flip-flop here. and T flip-flop here. In case of D flip-flop, what I'm going to do is I'm going to do a small change. I'm taking my JK flip-flop as it is, and your outputs also as it is. This is my JK. What I'm going to do, I'm going to add one NOT gate and connecting here. This single input now I'm calling it the D input. Okay, if you start, so this is my clock, positive edge triggered clock. So if I try to analyze this circuit, first clock will come, then D will come, then Qn plus 1 will come. When the clock is 0, irrespective of your D, whatever the D, it is going to be in the same state, or you can say it will be in the memory state. When the clock is enabled, when D is 1, you are going to have J equals to 1 and K equals to 0, because there is a NOT gate. When J is 0, K is 1, it's going to set the output. That means you are going to get the output as 1, or you can say set state. And the clock is enabled when D is 0. When D is 0, you are going to get J is 0, K is 1. In this case, you are going to reset your output. That means you are going to get 0 here. If you observe carefully, whatever the D you are given here, the same D is getting transferred to the output side. That's why it is called a transferent flip-flop, sometimes data flip-flop. This property will be useful in making the registers or designing the registers where you are going to store your bits. Please make this point. Your D flip-flop will be very useful when you want to store the information, either 1 bit or 4 bit or any number of bit. Based on that, you are going to take the different number of D flip-flops. This is all about your. Now let us simulate the D flip-flop here. If you look at here, your J and K are connected through a NOT gate. So this set 1 is nothing but your D input, and these are my outputs. Now let's run the simulation. So if you look at here, when data is 1, your output is 1, provided your enable is 1. If I make my data input to 0, my output will be 0. If I make 1, it will be 1. So whatever the input you give at data side, the same thing will be appear at the output side. The moment I make my enable 0, so irrespective, even if the data is 0 or 1, your output will remain in the same or memory state. The moment I enable my clock, it going to take whatever the D input given here, the same D input will be appear at the output side. So this is a simulation of your D flip-flop. Now we'll see the T flip-flop. T flip-flop is nothing but toggle flip-flop. So I'm going to do a small modification for my JK flip-flop to make my JK flip-flop to T flip-flop. So this is my J input, and this is my K input, and this is my Q, and this is my Q bar, and this is my clock. Now I'm going to short these two inputs, J and K, and I'm making this input as T input, and rest all will be same. This is a positive edge triggered. Let's take. Now let us analyze this circuit. Let's take clock, then T input, then Qn plus 1. If clock is 0, it doesn't have to care about the T input. It's going to be in the same state, that will be memory state. If clock is high, when T is 1, when T equals to 1, your J will be 1, K will be 1. So when J equals to K equals to 1 and clock is enabled, your output will toggle. That means your 0 becomes 1, 1 becomes 0. Now in the same way, when the clock is enabled, when T is 0, that means when T is 0 means you are going to have J equals 0, K equals 0. When both are 0, 0, it will be in the memory state. It will be in the same state as your previous state. So this is about your D flip-flop and T flip-flop. In designing, you are going to use 4 flip-flops. One is SR, then JK, then D flip-flop and T flip-flop. So I'm giving a small homework for you. There is a master and slave flip-flop. Please go through the books and figure it out what it is and what is the role of this particular flip-flop, what problem it is going to solve when you introduce this kind of flip-flop. Now I'm going to tell you asynchronous inputs for the flip-flop. Each flip-flop will have two asynchronous inputs. Please listen. You are going to have two asynchronous inputs to the flip-flops. These flip-flops will be useful in set your output to 0 or set your output to 1 depending on our requirement, irrespective of your input. Please remember this, very important. These asynchronous inputs going to set the flip-flop output to 0 state or 1 state irrespective of your input conditions. You don't have to care about the input condition. You can always set your flip-flop to 0 state or 1 state. So this will be useful. These asynchronous inputs will be useful to start your counter, to start the counter value from 0 onwards. And also sometimes we need to set flip-flop output to 0 to store a new information, also. So there are other applications. These are the two applications. In basically when you design the counter, let's say 0 to 9 counter, suppose you stop at 7 place. Now your flip-flop will store 111 in 3 flip-flops. Now if you want to start from 0 once again, what you do is you apply the asynchronous input to these particular flip-flops. It's going to keep all the outputs to 0. Then you can start counting once again 0 to 1, then 1 to 2 and so on. So these are the two asynchronous inputs. Those inputs are called preset. Those inputs are called preset and clear. So please make a note. Those two asynchronous inputs are called preset and clear. Now I am going to show you where these inputs will be applied to your circuit, how it is going to set your output to 0 without considering the inputs of that particular flip-flop. Now let us consider JK flip-flop. Now I am going to add two inputs to this flip-flop. One is preset, or sometimes called the preset bar. Other one is clear or clear bar. Both are fine. So what it does is, suppose let's take the conditions to understand what it does. Suppose if you make your preset bar to low and your clear to 1. Let us analyze this circuit. So if you keep your 0 here and 1 here, so since one of the input for the NAND gate is 0, it doesn't have to consider the other inputs. It will directly produce output as 1 here and 0 here. So that means whenever preset is low, it is going to set your output to 1 state. Now if you take preset bar to 1 and clear bar to 0, let's cross these things. Now I am applying, this is 1 and this is 0. In this case, this NAND gate will produce 1 here and you are going to produce 0 here. That means whenever you apply clear bar is 0, it is going to reset my output to 0 state. Similarly, If we make both 1 1, preset is 1 and clear also 1 or clear bar also 1, that means this is 1 and this is 1. In this case it has to wait for the other inputs to come because it is only 1. When one input of the NAND gate is 1, it has to wait for the other two inputs. That means whenever these two are 1 1, we are supposed to use a JK flip-flop up. When both are 1 1, you are going to use a JK flip-flop operation. That means your output depends upon the J and K inputs. The last condition where your preset bar is low and clear also low. So if you understand here, you are asking your flip-flop to preset as well as clear at the same time. So it will be contradictory instruction to the flip-flop, asking flip-flop to set to one state and clear to the 0 state. So we don't use this condition. Please remember, we don't use preset bar equals 0, clear equals 0 condition. We use only these three. One is when you apply preset 0 and clear 1, it is going to set your output to 1. Second one is you are going to apply preset to 1, clear to 0, it is going to clear the output. When you give both are 1 1, it is going to work as a JK flip-flop and your output depends upon the present input. These asynchronous inputs will be useful whenever you want to clear the registered data which already available on the output side. So this is all about asynchronous inputs to the JK flip-flop. In the next class, we are going to see the applications of JK flip-flop. Particularly, I am going to discuss the shift registers based on D flip-flops. So this is all for your flip-flops. Thank you all.